Okay, so let's get started. So it's the last session. I'm chairing again, just like at the start. And we'll have a review from Michel Lochner, who will tell us about machine learning for radio astronomy and transient. So Michel, I'll send you a message at 45. So please go ahead. Thank you.
Great. Thank you so much, Henry. So as I said, I'm Michel Lochner. I'm a senior lecturer at the University of the Western Cape, with a joint staff scientist position at the South African Radio-astronomy Observatory. And I'd like to thank the organizers for inviting me to give this talk. It's quite daunting to cover both radio astronomy and transients, but I decided to try and tackle it because, because I was asked to, and also because these are fields that I work in, I'm interested in, and I think it's quite interesting, almost from a sociological perspective, kind of seeing the differences in the use of machine learning in the two different fields, where it's become an absolutely critical part of almost every pipeline for transient astronomy, but the uptake has been slower in radio astronomy, kind of similar to exoplanets with Ingo's talk this morning. I will, like all the other review speakers, apologize to the many, many people doing great work in these fields that I'm not going to touch on. I'm not going to pretend this is going to be a representative sampling. It's very biased, and I'm trying to tell a story, and I'm trying to focus on a couple of aspects that I think maybe haven't been highlighted yet. So hopefully it's also something kind of interesting and different techniques-wise. Okay, so I'm going to start on transients, actually, although I'll spend most of the talk talking about radio astronomy. So there's a project that I'm very excited about. I think many of you are as well, which is the Virus-Rubin Observatory. This is a very recent picture of it. And this is under construction in Chile. It's a big international project, mostly led by the US, where the plan is to run this 10-year legacy survey of space and time. Now, this telescope has the biggest camera in the world and has a very wide field of view, can go very deep, and is very fast. And what that amounts to is basically being able to make a movie of a big chunk of the southern sky. So this is a simulation where every dot is a new supernova being discovered. And the number to keep in mind is that because of the properties of this telescope, every single night it will detect 10 million things changing on the sky. So that's 10 million alerts every night. And about half of those are actually going to be real astronomical objects. So it's an enormous data challenge, and I think the field is completely convinced that there is this powerful need for machine learning. So there's a massive amount of focus on machine learning in the field. So what kind of problems are there in transient astronomy? There are many problems, many different applications of machine learning, but I think the thing that's mostly worked on is classification. So we have to identify these transients before we can do anything with them. And coming from a cosmology background, obviously I'm particularly interested in type 1a supernovae as compared to all the other junk that nobody's interested in. Well, okay, actually as many astronomers interested in core collapse supernovae, but to us they're contaminants. So this is a very classic example of a classification problem that we want to solve in transient astronomy. And this is something I worked on as far back as 2016. So this is an example of what the data looks like. So remember that the Rubin Observatory is a photometric only telescope. So it has 6 bands on it. So it looks a little bit like this. So this is the brightness as a function of time in different bands. This is a simulated DES supernova, of course. So without spectroscopic confirmation, this classification problem becomes really difficult. So we only have this kind of data to classify the vast majority of the data set. These 10 million alerts every night, most of them we're not going to be able to follow up. So this is what we've got to work with. And by eye, it's very difficult to tell the difference between different classes of supernovae. But when we did this 5 years ago, we were able to use some call it shallow learning techniques. So we used a bunch of different feature extractors, eventually settling on these wavelets features. We looked at a bunch of different machine learning algorithms. Naturally, the ensemble tree methods went out. And we were able to do a reasonable job of classifying these supernovae. But as you saw in Katerina's talk yesterday, when you when you take into account much more realistic simulations, so the plastic simulations, which are, they have much more realistic models. They try to emulate the kind of data we expect from Rubin. So the cadence is kind of messy. There's missing data. It's a much more challenging data set. And I feel that I really like what Ingo said this morning about focusing on, publicizing failed results. So SN Machine, the beautiful classification pipeline that I built in 2016, failed out of the box on the plastic data. And it took Katerina's hard work to get it to work with this more realistic data set. And of course, most of the focus, there were some changes to the feature extraction, but most of the focus was in the data itself. So being able to do augmentation, interpolating better, using a more advanced version of the GPs, et cetera, et cetera. So I just bring this up. I think we've all been through this, where you have some great machine learning pipeline, does really, really well, and then you go onto the real data and suddenly it all falls down. And that's okay, that's just science. So there is always going to be this process of needing to improve the algorithms, and generally the focus is on the training data and improving the training data. But sometimes you have to tweak the algorithms themselves. Another thing that's interesting in transient astronomy that I think hasn't been mentioned very much is online learning. And of course, so what I've been talking about up until now is you've taken your 10-year survey, you have your nice big data set of light curves, and then you want to classify them. Sorry, am I the only one hearing it kind of static? Okay. I'm just going to carry on optimistically. Okay, so you've got your big data set of light curves and you classify them after the fact, and then you use them for something. And this is really important, particularly for cosmology, and this will be an important application for Rubin, but it's not the only way. We have, transients are real-time, it's real-time data coming in, and we want to be able to follow them up while they're still there on the sky. So in terms of wanting to do spectroscopic follow-up, we need to be able to classify early on before the entire light curve is finished. And this is where online learning comes in. And I just wanted to mention these brokers. This is an example of the Antares broker. It's just one of quite a few different brokers. And these are very complicated. You can see how complicated they are. Pieces of software that employ, among other things, a bunch of machine learning algorithms to classify objects as they come off the telescope. So as you get the alert stream in, it tries to tag the different objects. And this is going to be absolutely critical for the Rubin Observatory. It's already very important for the Zwicky Transient facility. And I wanted to highlight this because you often hear it said that industry is driving machine learning. And there are many aspects of that that's not ideal for science. Like, for instance, uncertainty quantification is more important to us than it is in industry. But I think this is an example of where we are actually taking the lead from industry, because these brokers and many aspects of these machine learning pipelines have become very industrialized. They're using a lot of tools. So this is a screenshot from the latest Antares paper. They're using a lot of tools that are developed and used in industry that we're kind of porting over to astronomy. And I know the same thing happens in complex cosmological pipelines, and I'm sure in many other places. So I just wanted to highlight this, that this is, as part of the machine learning ecosystem, we're kind of being forced to become more and more professional than perhaps we might like, and when we actually deploy these algorithms in a very practical sense. Okay. So that was what I wanted to cover about transient astronomy, not even an overview, just a few points I wanted to make. And I will mention transients again a bit later, but now I want to focus on the radio astronomy part, which is really the bulk of the talk. When it comes to radio astronomy, the instrument that's got everybody talking and everybody excited is the Square Kilometre Array. And this will be the biggest telescope ever built once it's actually built. And I'm specifically talking, whenever I'm talking about radio astronomy in this talk, I'm specifically focusing on interferometry, which is when you have arrays of antennas, and we basically correlate every pair of antenna to get them to work together to build up images of the sky. Now the SKA will consist of two instruments, the SKA Mid, which will be in South Africa, and the SKA low, which is like 130,000 of these little dipoles in Australia. So they're really two very different instruments, but they together present incredible data rates. You've seen that in one of the previous talks. The raw data that comes off of these telescopes is massive. It's much bigger than for any other type of telescope, as far as I know, mostly because you're having to correlate every pair of antenna for every time step. So you have this enormous, difficult to work with raw data. So the data processing pipelines are incredibly complex. And I think many of you are probably not very familiar with radio astronomy. I know a few of you are. But I wanted to, and I'll get back to that in a second. Before I go into highlighting some of the data challenges with what we'll expect from the SKA, I actually wanted to mention the fact that we are facing challenges today already before the SKA comes along. The precursors, the pathfinders to the SKA, kind of represent the step change in both quality of data and quantity of data. That's really forcing us to kind of change how we go about analyzing this. So the three precursors that I want to highlight are MeerKAT in South Africa, obviously very, very close to my heart, which is a very powerful world-class instrument in its own right. ASCAP in Australia is also one of these pathfinders. These are very complementary instruments. They have different strengths and weaknesses, both producing absolutely incredible data sets. And then, of course, we have LOFAR in Europe, which is the low-frequency prototype for SKA low. So these telescopes are already starting to challenge us, both when it comes to processing the raw data, but even working with the processed data, we have incredible numbers that we have to deal with. Okay, so what I actually wanted to mention when it comes to the radio astronomy challenges, to show those of you who maybe are not familiar with radio astronomy, what it is that we have to work with. I dug this out of my PhD. So this is a simulation from the Westerbork radio telescope. And this is what happens when you take that raw data that I talked about. You have to do a bunch of stuff like gridding it, and then you Fourier transform it to get this thing called the dirty image. And so this is what the beam looks like. So this is what the PSF looks like in the radio. So you have to do this deconvolution step, which is a bit complicated, in order to get out what's called the cleaned image so that we can actually work with it. And what I want you to notice is that the noise is very correlated, very complicated. We often end up with these artifacts in it. So even simple things like source finding can be quite challenging with radio astronomy data. And in some ways, this gets even harder. So this is an image from, this is a MeerKAT image from the MIGHTY project that just came out. There's the paper. And the noise properties are a lot better for MeerKAT. It's got a much, much better beam because it's got a denser array. It's nice and filled in. But it's also very sensitive. So we suddenly have source counts, the likes of which we're just not used to. So you can see in this image that we have a very high density of sources. We have confused sources. And incidentally, I think that the types of algorithms that are quite mature in the optical, like deblending, etc., haven't quite made their way into radio astronomy, or at least are not commonplace. I think there's a lot of opportunities for some of these clever algorithms to be adapted into the radio astronomy field. And I think we are starting to see a lot of that, which is really exciting. So we have these difficult data challenges just from looking at the images in the first place. We have other challenges with trying to introduce machine learning into astronomy. So this is a very nice paper where they were looking at a bunch of different CNN architectures that have been proposed in the literature for classifying radio sources. And they have a couple of classes, such as just a compact source, which is just an unresolved source, and the kind of two main classes of active galaxies, which are these FR1 and FR2 types. So Svanneroff-Reilly was the original classification scheme. So these are, FR1s is kind of when you see just kind of plain jets that don't end in these very bright lobes. Okay, so these are the kind of two main classes for this classification problem. Then you find something in some MeerKAT data, and I look at this, I'm like, I don't know what class this belongs to. So because of the increased sensitivity and resolution of the Pathfinder instruments, it's not like we've never seen things like this before. Of course we have with VLA, etc. But they're starting to become more and more commonplace. We're starting to see features that we have never seen before. We're starting to have to think about, what kind of classes do these things belong to? And actually, the F of Fanaroff-Riley, Bernie Fanaroff just recently published this paper where he was looking at MeerKAT and GMRT data and exactly asking this question of, okay, this original classification scheme, is it still valid? Does it make sense when you have X-shaped galaxies and, bent tails and whatever? And the conclusion was, yes, FR1 and FR2 does still make sense, but we may need to kind of rethink these things as we are increasing in sensitivity and sample sizes. And the other point that I wanted to make about this, which is really the challenge for machine learning, is not only that we're starting to see things that maybe we haven't really seen before, but what that means is that we don't have the training sets. So we don't have big labeled training sets, the likes of which we are seeing in data from MeerKAT, ASCAP, and LOFAR. And obviously, there's lots of work going into this. There's Radio Galaxy Zoo. There's the SKA Data Challenge, which is fantastic. But I think it is a limiting factor at the moment as to why machine learning doesn't tend to be integral parts of radio astronomy pipelines quite yet. But I think once we have these training sets, we will very quickly see more and more of these techniques being ported over. Another important problem where I think machine learning can and is playing a very important role is source finding. So source finding in radio astronomy is quite difficult. The source finding algorithms that we have, they work okay for point sources, but are really struggling to detect and cleanly detect some of these extended sources. And I mean, I know source finding is not really a solved problem in any field, so it's not surprising it's an active field of research. So a couple of years ago, I worked with a postdoc on source finding using a CNN as a source finder for some simulated MeerKAT data. And indeed, we found it does work better than the currently used source finders. But in this case, again, we came up to the problem of struggling with training data. We just used simulations. We just used point sources. So, okay, it was nice. The algorithm, we've had an algorithm. We designed it. It worked well. We published it. But at the end of the day, it's not really useful unless it can handle more realistic data. And I think this was a very nice approach taken with the Clarin source finder. They used one of these region CNNs where they actually are a trained neural network trained on these types of objects and can actually not only classify the objects but also pick out where they are. So it's a source finder that's aware of extended sources. And of course, I don't want to steal any thunder. There's a couple of talks today about, I'm sure, really amazing source finding techniques using machine learning. And I think this is definitely the way to go. I think it's just difficult to really design an out-of-the-box source finder that's going to do a good job at finding these kind of sources. But again, the challenge is the training data. There really just is not that much training data for these. But that's something that's only going to get better soon. Okay, so speaking about the training data, what I wanted to move on to and really spend most of the time talking about today is unsupervised learning. And I thought this was a great example because SOMs have been the real talk of the town this conference. Things that Elizabeth said and others have said have made me all excited about SOMs again, so I'm gonna go tinker around with them. And I think this is a really lovely example of unsupervised learning applied to LOFAR data. So this uses Kai Polster's PINK algorithm, which is a deep rotation invariant self-organizing map. So I think it's particularly powerful when it comes to images. And I couldn't help but show a shot of what some of the beautiful LOFAR data looks like. And what you see here on the left is various radio galaxies in LOFAR data organized according to where they end up in the self-organizing map. And then they applied I think it was k-means in this case, to try to cluster the data. And you can see that they've colored the various squares with some kind of classification scheme and you can see that they are visually kind of similar. But I think this is a very interesting point when it comes to how do we classify things? Like, how do we come up with classification schemes that are sensible? Because this is clearly going beyond FR1 and FR2, right? And you know, we know something about the physics of what's going on in these things, but it's not clear that we have a predefined, a well-defined classification scheme. And I was reminded of Frederick Corbin's talk way back on Monday, where you have 7 experts and a very clearly defined classification scheme for strong lenses, and still none of them could agree with each other. So this is an interesting aspect when we are pushing the limits of technology. So we have telescopes that are observing things that we haven't really seen before. So it's a perfect use case for unsupervised learning. But there's always the and then what step, that we have to then do something with these clusters, with the things that we find. And sometimes that and then what step may actually be to come up with new classification schemes that might be suggested in these data-driven approaches. But I always think this type of unsupervised learning is a step that then needs to lead to other steps. So a great example would be, we come up with a classification scheme, we use the unsupervised learning to help us build training sets, and then we can train dedicated algorithms that we can test the accuracy of in order to do population science, for example. So I'm really interested in how we use these in a very practical sense in doing science with data sets that are unlabeled. And this is key in everything else that I want to talk about, that there really needs to be a human at the heart of machine learning. I think this is something that Mark said on one of the early days as well. We know that the human makes all the important decisions, particularly what training data to give the algorithm, for example. But I think when it comes to these types of unsupervised learning approaches, the human plays an even more critical role in interpreting what the algorithm outputs. And so we come to a branch of machine learning called active learning. And there's actually already been quite a few mentions of active learning in quite a few talks, particularly talks that are using machine learning algorithms in pipelines, in real data. They always end up needing to be this feedback loop of humans taking the candidates and actually vetting them from the machine learning algorithm. And then ideally, as you can see in this loop here, feeding it back into the training set. So Emily Ishida and her collaborators have done a lot of work on active learning for transient astronomy. And so the key thing is that you need to use some kind of criteria to decide. Basically, you run your machine learning algorithm, then you use some sort of criteria. And it's usually something like, which objects is the algorithm least certain about? And then you have to figure out how to get a label for those particular objects. In her case, she's interested in doing spectroscopic follow-up. So we take a spectrum of that object in order to improve the algorithm. But in some cases, it might be as simple as a human just looking at it and saying, yes, this is A or B. And when you add it to the training set, you can then improve your model. And I haven't actually seen the talk about this. I don't know if it's still coming or if it's passed and I missed it. But this astronomical, astronomic AL interface looks very promising. If you already have done the hard work of getting features out of your data, then you can run this, this interface to be able to very quickly label objects, retrain them, retrain your algorithm. And I think the active learning approach, to me, is just such an obvious way to do things. You don't have to laboriously label 100,000 random samples in your data set. You can start very small and very quickly improve your algorithm using active learning. So we can basically make better use of the expert time with cool interfaces like this. And then I also just wanted to highlight this paper by Chris Fluke and his team on, I think it's a cool phrasing, the cyber-human discovery systems. But the interesting idea there is we're dealing with these enormous data sets and very high dimensional. So how do we visualize them in such a way that we can make the best use of human intuition and creativity to identify weird things, to look for patterns, to look for anomalies, etc. So it's less about can you still hear me?
Yeah, you dropped out there for like 2 minutes, but it's okay now. 2 seconds, 2 seconds.
2 minutes.
2 seconds,
Oh,
2 seconds.
Okay. Okay.
It's been a long conference.
I'm going to have to go back a bit.
Long conference.
All right, cool.
Time dilation.
So okay. I'm going to carry on. Can you hear me?
Yeah, it's fine for the time being.
Perfect. Okay. If it gets really bad, you can play the rest from the recording. Cool. Okay, so what I really wanted to focus on is a different aspect of unsupervised learning, kind of bringing in together these threads, unsupervised learning with active learning. And it's a field that I'm very excited about, which is anomaly detection. So I think we all have an intuitive sense of what an anomaly is. It's anything that's rare or unusual or different from the norm in the data set. And there are many anomalies that we know about and we know how to look for. Like, for instance, there's been a lot of discussions of strong lenses in this conference. And so there's still anomalies, and they still are difficult because we may not have enough of them to build good training sets. So these are things for which anomaly detection algorithms can still be useful. But what I'm really interested in are the unknown unknowns. So the truly unexpected scientific discoveries. And I think a great example of this is the discovery of the pulsar in 1967. So this is a groundbreaking discovery in radio astronomy. And what it took was a very bright graduate student, Jocelyn Bell Burnell, manually looking through her data and seeing something weird and going, what's that? And I think most scientific discoveries are done this way, right? You look at your data, you find something weird, and it turns out to be a discovery. So the question is, how are we still going to do this when there's 10 million transient alerts every night? When there's 1 billion galaxies in your data set? How do we automate the process of scientific discovery? Now, this is where machine learning can play a useful role. There's a few different anomaly detection algorithms. There's ones that try to... The general idea is your data is unlabeled. So what the algorithms try to do is kind of learn what normal is and identify things that are kind of far away from normal. And so 2 classic examples that are used a lot are isolation forests, which is based on random forests. So the idea is to just isolate each point, and if it's very easy to isolate, like this one, then it's probably an anomaly. An alternative approach is local outlier factor, which basically just tries to find points in low-density regions of the feature space. So I've worked as part of teams on a couple of different anomaly detection algorithms, some novel approaches. I particularly like BADAC. It's a Bayesian anomaly detection and classification algorithm. And the nice thing about this is it's able to take into account uncertainty information. And then another technique invented by collaborators of mine is called DRAMA, which is a deep learning approach, which I think essentially just finds a sensible latent space representation and looks for anomalies in that latent space. But when Bruce Bassett, my collaborator, and I were talking about this a couple of years ago, what we realized pretty early on is that anomaly detection alone isn't actually enough. So, for example, the difference between anomaly detection and classification is once we've all agreed on a classification scheme, then it's pretty simple that this is a spiral galaxy and this is an elliptical galaxy. It's a clear definition. But while there may be many artifacts, it's not clear. I mean, obviously not all of them are useful, and whether or not they're useful kind of depends on what's your science case and what's your interest. So for example, here, as an astronomer, I might be more interested in real sources than in artifacts. But if I'm focused on checking the data quality, then I might actually prioritize and really want to know about the artifacts and not care about anything else. And even different scientists will have different scientific interests. So what's interesting to me may not be interesting to you. So there's this kind of inherent subjectiveness in not necessarily the anomaly detection step, but in the and then what step? What do we do with them? And so what we realized we wanted was kind of like a recommendation engine for anomalies. So this is where active learning plays a role. So where you can use your expert to label some data to identify what's actually interesting to them to build a recommendation engine. And so our attempt at doing this is called Astronomaly. So it's a framework with a Python backend and a JavaScript frontend. And the Python backend is a pretty straightforward machine learning pipeline. So it can take in data, and it can take in basically more or less any kind of astronomical data, images, be it optical, radio, whatever, time series data, spectra. And there's several feature extraction methods, and obviously it was designed to be modular to add more, and I'm going to talk about a really nice method right at the end. There's a couple of different anomaly detection algorithms you can choose from, but the key part about it is this loop, this human labeling and detection loop. So the interface that you can see here allows you to very quickly look through the data, and at no point do we say this is an anomaly or this isn't an anomaly. We just rank the data according to most to least anomalous and order it so that you can focus your time on the anomalies, but you use these buttons to label the data to say whether it's interesting or not. And then we've developed a novel active learning approach to improve the algorithm to be better at presenting to you the things that are actually interesting. And I just want to highlight that this algorithm works by if a new object comes along which has a very high anomaly score according to the machine learning, if there's no labeled data nearby, then you're going to see it. So we didn't want to run the risk of missing out of interesting anomalies, but basically all it really does is anything that you've said this is not interesting and something similar crops up, it will just downweigh that, and that goes kind of down the list. Anyway, the paper is out and the code is publicly available. It's very much in development, just as a warning, but I'd be absolutely delighted if anyone wants to start playing around with it for their data. And obviously, I'm happy to help with user support. Okay, so let's see this thing in action. So I used the Galaxy Zoo dataset. I'm sure you're all familiar with Galaxy Zoo. So what we did is here you're looking at just a random ordering of the data. So what you mostly see are ellipticals, spirals, etc. And then do a feature extraction, and the features I use are actually extremely simple. They're kind of stupid in a way, morphology features, but they are very fast, which are just based on fitting ellipses to isophotes, essentially. And run the machine learning algorithm, in this case, isolation forest. And then if you order the data from most to least anomalous, it actually does surprisingly well, given the simplicity of the features, that it picks up objects that have interesting morphology, they're mergers or tidal streams, etc. But it does also pick up some anomalies, some artifacts. So what you see at the bottom with the buttons kind of changing color, I'm labeling the data according to how interesting I find it, and then I can run this novel active learning algorithm and order the data according to the new score. And what you see is that the artifacts tend to kind of have been pushed further down the list. So I'm seeing more of the types of objects that I'm interested in and less of the objects that I'm not interested in. And of course, I'm supposed to be talking about radio astronomy, so let me show you a radio example. So this is a MeerKAT survey of a bunch of clusters. So this paper is in review, it's nearly out. And again, what I've done is I've taken the images, taken the sources, and I'm just showing you a random sampling of sources. So you should be focusing on the center. They're mostly just kind of point sources. But again, if I use exactly the same algorithm and order from most to least anomalous, what we get out are things with much more interesting morphology than point sources. It does a reasonably good job at picking out these kind of weird extended sources that we can then use for other things. And here's just kind of a wallpaper of the top 10 anomalies from that data set. I think this one's my favorite. So yeah, okay. Cool. So in the last few minutes, what I want to cover is a couple of interesting applications that I think highlight, I'm obviously biased because these are all projects I've worked on, but I think they highlight different aspects of machine learning that are of general kind of interest. And the first one is work done by Sarah Webb, who's now a postdoc in Australia. So she came to me a couple of years ago with this huge data set of like 1 million light curves. Well, we actually focused on about 80,000 of them. And this was taken from the Deeper, Wider, Faster program, which is a multi-wavelength program trying to look for fast transients. So these are things changing on the scale of like a minute. And so she had this big data set, and it was unlabeled. Nobody had really looked at it. She didn't know how to tackle such a large data set. So we did a completely unsupervised end-to-end pipeline, and it was nice that we went from raw data to science pretty quickly using unsupervised learning, so without having to label terribly much. And what she did was just use a very simple feature extractor that's commonly used in transient astronomy called FEAT. And she used clustering, in this case HDB scan, to identify the majority of sources. And most of them were just ordinary stars, so not doing anything. A huge number were different types of artifacts. And then there were some interesting smaller clusters that were variable stars, etc., and then some kind of unknown things. And that's what she ran Astronomaly on. And it was quite good. So she picked out a couple of known variable stars, but also made some discoveries, so some new variable stars, and also this quite weirdly behaving flare star. So like I said, it was a nice example of how you can go from data that you almost don't really know anything about. You have to know a little bit, enough to do feature extraction, use unsupervised techniques, and get out to some science and actually do something with it. But then I wanted to give an example of a case where machine learning didn't work so well. Again, I think what Ingo said this morning was really important, that we should really be talking about the times when things don't work very well. And this was in the problem of real-time anomaly detection. So as I said in the beginning, it's all very well and good to classify a data set of light curves. That's really important. So like what Sarah did and what we've done with Katerina. But we also need to be able to operate in real time, because if we detect an anomalous transient, blink and you'll miss it. You've got to be able to follow it up while it's still out there, while it's still doing something. And again, this is a real needle in a haystack problem. We've got 10 million alerts coming in every night. We've got to figure out which of those are actually interesting enough to follow up. And so I came up with an idea that was extremely simple. We know a fair bit about transients, so we have a fair bit of data. So we know roughly what a type 1a supernova looks like, what a type 2 looks like, etc. So if we can model these light curves, and we can, given a few points on a light curve, make a prediction for the next point. If then the real data is very different from that prediction, well, maybe it's an anomaly. Very easy idea. And so I worked with a then student, he's now a postdoc at MIT, Dan Mitch-Krishna, on adapting his classification algorithm. So he had an RNN classification algorithm called RAPID. So turning it into a regressor, essentially, to be able to predict the next data point. And he ended up rewriting the architecture completely using a temporal CNN, but did a pretty good job. And what you can see here is that the gray band is simulating taking new observations and giving them to the algorithm. And at first, there's several realizations. So at first, it's extremely uncertain. But as you take more and more data, it does a better and better job at actually predicting the next points in the light curve. The trouble is, it works too well. So in some sense, even though it doesn't. We would, for instance, take the type 1a supernovae and just train it on that. It was able to predict what type 1a's do, but it was also able to predict what anything else does. So it actually didn't. It was too flexible to work well as an anomaly detector. And in fact, he tried really hard to make it very Bayesian. So using dropout, adapting the cost functions, and other things I can't quite remember, but really trying to get good uncertainties out of this network, and it was still overconfident. So this is a case where, I mean, you probably could get it to work, but it just didn't work that well. And what did work well is the good old Bayesian approach. So here, these are very complicated plots, but basically on this side are all the normal classes. So here we expect things to be kind of blue. And on this side are all the anomalies where we kind of expect things to be red. We expect to have a high anomaly score. And you can see for the deep learning, except for a few classes, it's sort of able to fit anything. Whereas with this, this is a parametric model that's then fit using training data. The prior is learned using training data. And so then it's able to predict in pretty much the same way. It does a better job for most of these classes at realizing that these are anomalies. So you could probably get this to work. I'm sure there's many clever people in that room and watching online. I'm sure you could get this to work, but it was one of those cases where actually the Bayesian approach was just more natural and did a better job in this case. This paper should come up very, very soon, probably next week. So just keep an eye out for it. And then finally, this is something very new that I'm very excited about. So this is work done by Mike Walmsley. So when we started working together, he was a student, and now also a postdoc at Manchester. And he saw what I did with Astronomaly, and he thought, oh, that's quite cool. I'm sure I could do it better. And he was completely right. And what he had was, so he'd taken the latest version of Galaxy Zoo, which uses decals data, trained a CNN to do the classification. Now, if you're not familiar with Galaxy Zoo, the classification scheme is very complex. So it's not just, is it a spiral galaxy? It's, is it a spiral galaxy? Does it have bars? Is it a flocculent? Is it, et cetera, et cetera? So it's quite sensitive. The classification tree itself is quite sensitive to the morphology. And so what Mike did is he trained a CNN to be able to classify all the galaxies in this data set. And then you actually use that as a representation for other tasks. So you use the deep features to be able to perform things like anomaly detection. And the cool thing is that this was trained using decals data, but we applied it to the old Galaxy Zoo data, which was SDSS, and it worked really, really well. Something that I found quite interesting, okay, so just to show you that it works, these are the percentage of anomalies that you found so far as you go through the index, and this is the index. So the red is random. This was what we did with the simple morphology features, and this is an insane amount better with the CNN. And what was interesting, I thought, is that if you look at a UMAP of this feature space, it's quite different from the simple features that I had. And iForest actually really didn't work very well here, because iForest kind of expect things, the anomalies, to really be anomalous and be on the edge of the space and look quite different. Whereas the CNN was much, much better at grouping similar objects together. So it's much better at identifying these are all mergers or these are all tidal streams, whatever. But they don't really crop up as, you know, on the edge of feature space like we might expect. So Mike came up with a very nice approach, a kind of an alternative approach to the way we implemented the active learning, using a GP to basically, as a regressor, to predict where the user, where the user thinks things are interesting. And then it uses a more traditional active learning loop to improve that. So, I mean, it's a lesson that I think we probably all know, but if you are using shallow, well, this is kind of deep plus shallow learning. But if you're using a set of features, make sure that you're using an algorithm that is well matched to the way those features represent your data. But I'm very, very excited about this. I think this is the way to go, and it will be in Astronomaly quite soon, I hope. I think Mike's online, so if you want to chat to him more about this, please do. I think that he tried to put the paper on the archive, but there was some technical glitch, so it should be out like on Monday, I'm sure. So keep an eye out for that. It's pretty cool work. Okay, so to finish off, let's think a little bit about, cool, perfect. So let's think a little bit about where things are going. And I kind of touched on a bunch of concepts. I'm trying to talk about things that are a little bit different from what has been brought up so far. It's the advantage of going last, that I get to see what to avoid repeating. But just thinking in terms of very, very practically, how do we bring machine learning into our pipelines to do really great science and to use some of these kind of more novel approaches? So the one thing I wanted to highlight again is this kind of industrialization that is already happening all over our field. I think is being very well embraced, but using the kind of tools that already exist in industry and applying them into astronomy. I think unsupervised learning is a fantastic tool, especially in the regime that we often find ourselves, especially in radio astronomy, where technology has opened up a window to the universe that we didn't have before, which means there's a lot of opportunity for discovery, but we just don't have the training sets yet. And so this can be used, I think, to great effect. I'm excited about representation learning. I think Mike's approach is really cool. And he raised this nice point in the paper, which is that maybe with these kinds of trained networks that are trained on a specific task, but which is quite general, such as morphology classification, and can then just be used for other tasks, so that not only are we reusing the architecture, but we can actually just reuse the network. For me, who just wants to use these things, I think it's a nice approach. Of course, we have to be careful. We know that transferring algorithm from one data set to the next can induce all kinds of idiosyncrasies. So we have to keep an eye out, but so far this looks very, very promising for anomaly detection. And then, of course, active learning, bringing that human in the loop is really critical. We always need to give these algorithms some oversight. At the end of the day, it's always got to be a human making these decisions. And the real question is, how do we combine the machine and the human the most effectively to kind of minimize the amount of time that we're wasting and maximize the science? So at the end of the day, these kind of techniques are not the same types of very beautiful precision techniques that have been mentioned throughout the conference. These are really practical techniques to help us just get to better science faster. And that's kind of the regime of machine learning that I've been particularly interested in. In the last 2 minutes, while I have your undivided attention, I wanted to advertise two things, just completely abuse my position as speaker. The first is I run the Supernova Foundation, which is a mentoring program for women and gender minorities in physics. Here's a screenshot of some of our wonderful mentors from all over the world. So if you're interested in becoming a mentor or mentee, please do think about applying. There's a website. And finally, I also wanted to advertise a postdoc starting in 2022, specifically working on anything vaguely related to Rubin and machine learning. I'm pretty flexible. As you can see, I have quite varied interests. It's difficult for me to compete, or for Cape Town to compete with places like Paris and MIT, etc. I know it's kind of halfway around the world for most of you. So I thought the most sensible thing to do was to give you a very unbiased representative sample of what Cape Town looks like.
Yeah, where's that beach?
Actually, I've actually taken all of these photos. So this is an unbiased view of Cape Town. This is a beach about 15 minutes drive from me called Milnerton.
Wow.
It's actually where I got married. So yes, so this is my advert. So please, if you are a young person interested in these topics, do think about applying. If you are a yet less than young person, but you know a young person interested in these topics, please let them know about it. And to finish off, I wanted to think of a pearl of wisdom to pass on to the younger generation. I thought of something and I thought it's way too corny for me to say, but a friend of mine convinced me to say it. So if it's really horrible, just blame her. My advice is put a human at the heart of machine learning and put science at the heart of the human. Thank you very much.
Great, thank you very much. So, Michelle, there were so many interesting things in your talk. It woke everyone up after the hard drinking everyone did last night. Can I just abuse my position as chairman to ask you, what were all those strange objects that you showed us in the anomaly detection? The long extended objects, what were those things in the end?
Yeah, these things.
Can you go back to the slide?
Is it this one? Can you see?
Yeah, the red things.
Can you still see my screen? Sorry.
No, we can't.
Still share. I'm stuck. Sorry.
Yeah, from the MeerKAT.
There we go. So these are cool. So they're all active galaxies. So in radio astronomy, like everything we see is not what we consider a normal galaxy in optical. So they're all active galaxies with nice big jets, and some of them are kind of normal. So they're somewhat normal-looking radio galaxies, but some of them are kind of crazy. And in these cases where they're kind of weird bent things, they're generally interacting with the intergalactic medium. In this case, this is something that's in the center of a cluster. So there's loads of interaction going on with all the gases, et cetera, et cetera. But I think there's still a lot to be done in understanding all the physics that's going on in some of these weird objects, particularly as we've increased sensitivity to them. So there's new discoveries happening all the time.
And those were known jets, were they?
Some of them were known, but some of them I think are new objects. I don't actually know. I haven't. Yeah. There's so many that I haven't actually in detail looked at every single one yet. Okay,
great. So just in passing, how many sources are in the Cosmos image in the MeerKAT survey that you showed? I'm just abusing my position as the chairman here.
The number. Okay, I'm probably wrong, but it's something like 40,000.
Okay, that's
it's several thousand sources in that single image, yeah.
Okay, so how many, is there any questions in the audience? There's one question already on Slack. So the question on Slack is from Fiona Porter. Thanks for the talk. I was wondering if you had any thoughts on using GANs to emulate extra galaxies to extend small data sets. One of my former co-workers did some work and we found it very hard to tell simulated FRs from real ones.
Yeah, I think that's a really cool idea. And of course, Mark Hurta's company has also worked on using GANs in the optical, particularly for anomaly detection. So if you can use GANs to kind of simulate normal galaxies, then things that don't tend to fit well should be abnormal. And you've also got this nice kind of feature extractor that you can use. So yeah, I think I haven't tried it. I've done mostly very simple things on lots of different data sets rather than complicated things on one data set. But I think it's a very cool approach, and I think it's an obvious direction to try.
Yeah, so we have a question from the audience, so just state your name and your question.
Hi, I'm Mike Smith here. Great talk. I'm interested in Mike Walmsley's CNN representation learning thing. I was wondering if you could talk a bit more about the architecture. Does he just take the penultimate layer and use that as an embedding vector?
That's probably better directed to Mike, who's on Slack, who will
on the Slack, yeah.
Have this at the tip of his fingers. Mm-hmm. So it is definitely taking the last layer, but if I remember correctly, he did do another step of dimensionality reduction to get it down to, I think it was 128 dimensions. But it is literally, the core set of features is just chopping off the last layer of the network and using that as a representation.
Oh, cool. Thanks.
Yeah, Mike has just posted some GitHub links to his work on the Slack.
Yes. Thanks, Mike.
There's another question here, yeah.
Karen Henneke, hello. So regarding the unsupervised learning, I'm curious. So for example, for the T-SNE maps, you have like these human steps of basically flagging kind of the regions, I guess. And you said you kind of advocate for putting the human at the heart of the machine learning. So what do you think of approaches to try to automate this flagging? Like, I don't know, for example, for T-SNE, the parametric T-SNEs?
Yeah, I think it's all about using the human most effectively. And this is where I think the unsupervised approach is great. So I tend to use TSNE or UMAP just as visualization tools. Because of the stochastic nature of TSNEs, I don't often use them any further than that, but you can, and you can use UMAPs in the same way. So in this case, for instance, what Sarah did is using a feature extractor, and then this is obviously the visualization of the features. But then the unsupervised step from there is doing clustering. So in this case, an algorithm called HDB scan. And what you can do is, I think this is very effective because you can have a whole cluster and you can look at examples of the cluster and you can say, all right, these pretty much all look like X. They all look like this particular type of artifact. Let me not pay too much attention to that cluster. Obviously, you're going to miss a few. It's not going to be 100% accurate, but this is very fast. So you can, she in one step disregarded like 50,000 light curves just from looking at these clusters in the machine from the clustering algorithm. So I think that's the thing that's really fast. It's not, like I said, it's not necessarily going to be as accurate as a very carefully curated classifier, but it means that you can spend your time focusing on the more interesting clusters where you're finding more unusual objects. I don't know if that 100% answers your question, but that's kind of what I think on the topic.
Okay, thanks. Yeah.
Some more questions in the audience? Some questions on Slack?
Mike answered the question.
There was a question from Mike, yeah. He says it's chopping off the last layer with 2 twists, so read the comment on Slack.
Thanks, Mike.
Yeah. Guillaume, no?
Yeah, so Guillaume Lavaux. So you showed like this failure of anomaly detection for like supernovae light curves, but you didn't necessarily like detail a little bit more about what was used as a model for this light curves. I guess it's a long-term Lochner memory of some kind, and
yeah. So what Dan used in that case was actually this temporal CNN, so TCNs. Which I hadn't heard of before he introduced me to it. But the idea is that it's basically a CNN, but designed for one-dimensional data, so for time series data. So he interpolates the few points of the light curve that you have in the different bands, and then applies the TCN architecture there to actually do the prediction for the next point. So the actual full details of the architecture are in there, but he found that this was easier to train and more reliable than the LSTMs. So in terms of an interesting algorithm for time series, I think it is quite a cool approach to use TCNs.
Okay, thanks.
Are there any more questions? Okay, so thank you again, Michelle. That was super interesting, and please follow the comments on Slack.